In this video, we're going to talk about the interconversion of potential energy and kinetic energy. This is one of the fundamental principles in physics and helps us understand how energy changes form while still being conserved. Let's start by considering a simple scenario. We have a body with mass m at rest at a height h above the surface of the Earth. At this initial position, which we'll call point A, the body has potential energy equal to mgh, where g is the gravitational acceleration, and its kinetic energy is 0 because it's at rest. Now, let's release the body and see what happens as it falls. As it falls, it loses height and gains speed. Let's say it reaches point B after falling a distance x. At this point, the height from the ground is h minus x. The potential energy at point B is therefore mg times h minus x. To find the kinetic energy, we need to calculate the velocity at point B. We can use the equation of motion. V final squared equals V initial squared plus 2 times g times displacement. Since the initial velocity is 0 and the displacement is x, we get VB squared equals 2gx. Plugging this into the kinetic energy formula, 1/2 mv squared, we get kinetic energy equals 1/2 m times 2gx, which simplifies to mgx. Now, let's look at the total energy at point B. The total energy is the sum of potential energy and kinetic energy. Substituting the values we just calculated, we get mg times h minus x plus mgx, which simplifies to mgh. This is exactly the same as the total energy at point A, which was mgh. This demonstrates the conservation of mechanical energy. As the body falls, potential energy is converted into kinetic energy, but the total energy remains constant. Let's continue tracking the body as it falls all the way to point C, which is at ground level. At point C, the height is 0, so the potential energy is 0. To find the kinetic energy, we again use the equation of motion. Since the total displacement from A to C is h, we get Vc squared equals 2gh. Substituting this into the kinetic energy formula, we get kinetic energy at C equals 1/2 m times 2gh, which simplifies to mgh. This means that at point C, all the potential energy from point A has been completely converted to kinetic energy. The total energy is still mgh, demonstrating energy conservation throughout the entire fall. Let's visualize how this energy conversion happens as the body falls. To make this clear, I'll draw a new diagram. On the vertical axis, we'll represent height, and we'll use the horizontal length of these bars to represent energy. At point A, the body has only potential energy and no kinetic energy. As it falls to point B, some potential energy converts to kinetic energy. Finally, at point C, all potential energy has been converted to kinetic energy. This gives us a general formula. The loss in potential energy equals the gain in kinetic energy, or mathematically, mg times h1 minus h2 equals 1/2 m times v2 squared minus v1 squared. So far, we've considered an ideal case with no friction. But in reality, there's often friction opposing the motion. When friction is present, part of the potential energy is used to do work against friction. If a constant frictional force F acts over the displacement h, the work done against friction is F times h. Our conservation equation then becomes loss in potential energy equals gain in kinetic energy plus work done against friction. Mathematically, mgh equals 1/2 m v squared plus fh. We can rearrange this to see that the kinetic energy at the bottom is less than the initial potential energy because some energy was lost to friction. To summarize, the interconversion of potential energy and kinetic energy is a direct application of the law of conservation of energy. In an ideal system with no friction, the sum of potential and kinetic energy remains constant. In real systems with friction, some energy is converted to heat, but the total energy is still conserved. This principle has many practical applications, from designing roller coasters to understanding how hydroelectric power plants work. Understanding energy conversion helps us analyze and predict the behavior of objects in various mechanical systems.